In this video, I'm going to talk about the structure and properties of alcohols, and I'll also be going over how to name alcohols. The first question is asking us to propose an explanation for the observation that alcohols that have more than 8 carbon atoms are not soluble in water. Let's begin by drawing a small alcohol, this little 2-carbon alcohol right here. This alcohol is soluble in water. The reason that it's soluble in water is because it has this polar OH group at the end of the molecule, and that polar OH group can hydrogen bond with water. This makes it soluble in water. Even though there are 2 carbon atoms, which are nonpolar, the very polar OH group kind of drags these 2 carbon atoms into the water solution and allows it to dissolve. As we increase the number of carbon atoms in this alcohol, the OH group continues to be polar, but it just becomes increasingly difficult to get those carbon atoms to dissolve. And as the carbon chain gets larger and larger and larger, eventually we reach a point where we have so many carbon atoms on the molecule that the nonpolar area of the molecule is no longer able to be drug into the aqueous solution by the polar OH group. So once we get to a point, this magic number seems to be 8, once we get to a point where we have 8 carbon atoms in the molecule or more, that just is too much. So this would be too much nonpolar, not soluble in water, despite the fact that we have the polar OH group. Different textbooks have different cutoff points for the solubility of alcohols in water. The textbook that I use gives 8 as the limit for the solubility, but you might see a slightly different number. The next question is asking us to rank these alcohols in order of increasing solubility in water. Increasing solubility. And again, this has to do with the number of carbon atoms on the carbon chain. The more carbon atoms there are, the less soluble it is. So this is going to be the least soluble out of all of these alcohols, just simply because it has the longest carbon chain. We're going to give this a number 1 because we're ranking them in order of increasing solubility. This molecule, which has the second largest number of carbon atoms, is going to be our next least soluble. And this will be our third. And this molecule, which only has 3 carbon atoms, will be the most soluble. And again, this is simply about the number of carbon atoms on the chain. Now we're going to think about the boiling point of these substances. We have 3 molecules that have approximately the same molecular weight, but really different boiling points. And we want to explain this observation about the relative trend in their boiling point. Boiling points are dictated by 2 factors. Boiling points are dictated by the weight or the mass of the molecule. If it is heavy, it's going to have a high boiling point. Because all of these substances have approximately the same weight, that's not going to be a factor in this problem. The second variable that dictates boiling points is the intermolecular forces. Strong intermolecular forces give us high boiling points, and low intermolecular forces give us low boiling points. This alcohol has a very high boiling point because it has strong intermolecular forces, specifically because it can hydrogen bond. The molecule in the middle, which doesn't have any hydrogen bonding, but it is polar, has the intermediate boiling point, and the first molecule, the alkane, because it is completely nonpolar, has the lowest boiling point. Now we're going to look at some naming. A phenol is a benzene ring that has an OH group attached. This is what we would call a phenol. It's pronounced phenol. 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 When we are naming phenols that have other things attached to them, the carbon that has the OH group is by default always going to be carbon number 1 on the benzene ring. And the other carbons are numbered in a way to give the other substituents in the molecule the smallest possible number. So this molecule right here, which is a phenol that has a chlorine on carbon number 3, is referred to as 3-chlorophenol. Remember that when we're numbering a ring, we can number clockwise or counterclockwise. It's our choice. We want to give our substituents the smallest possible number. So this would be called 2-ethyl phenol. And for this one, we are going to want to think about if we should be numbering clockwise or counterclockwise. If I number clockwise, the substituents, the methyl will be on 2 and the bromine will be on 5. If I number counterclockwise, the bromine will be on 3 and the methyl will be on 6. Just as a reminder, the way that we can determine the best possible set of numbers is by adding the numbering of the substituents. So if I number clockwise, which are the numbers in this red color, 2 plus 5 is 7. If I number counterclockwise, which are the numbers in blue, 3 plus 6 is 9. So that means we don't want to be using the blue numbers, we want to be using the red numbers. So we have a phenol that is substituted with a methyl group and a bromine group. Remember that substituents are listed alphabetically, so that means 5-bromo comes first in the name, and then 2-methyl, and then we just simply say phenol. For regular alcohols, we will, this would be an alcohol that is not on a benzene ring. We will name the alcohol by finding the longest carbon chain that contains the OH group. Not necessarily the longest carbon chain in the molecule, but the longest carbon chain that contains the OH group. So for this first example, the longest carbon chain that contains the OH group is this chain right here. Once we've identified the longest carbon chain, we'll number it in such a way to give the OH group the smallest possible number, because the OH group has priority in the naming of this molecule. We then reflect the fact that this molecule is an alcohol by dropping the E from the ending of the name and replacing it with all. A 3-carbon alkane would be propane. To name this as an alcohol, we just drop the E and we replace it with OL. So this would be propanol. We locate the position of the alcohol either at the front of the name, 2-propanol, or in the middle of the name, propan 2-ol. For cyclics, we do the exact same thing. We find the longest carbon chain that contains the OH group. We number the ring so that the OH group has the smallest possible number, and then we continue numbering clockwise or counterclockwise to give the rest of our substituents the smallest possible number. This is a cyclopentane. As an alcohol, it's a cyclopentanol, and there's a methyl group on carbon number 2. Remember, with cyclics, it's not necessary to locate the position of the OH group, so we don't have to say 2-methyl, 1-cyclopentanol. That would not be necessary. Here's another example. Let's begin by finding the longest carbon chain that contains the OH group and numbering that carbon chain to give the OH group the smallest possible number. Now we can name our substituents, a methyl group on carbon number 2, and the alcohol, which is also on carbon number 2. This is a 4-carbon chain, which would be butane. With the alcohol, it's butanol. Last but not least, we have looks like 1, 2, 3, 4, 5-carbon chain. We're not necessarily looking for the longest carbon chain, we're looking for the longest carbon chain that contains the OH group. We want to number this carbon chain to give the OH group the smallest possible number. So we're going to number it like this. And then we're going to name the location of our substituents. Our substituents are a methyl group on carbon number 4 and an ethyl group on carbon number 2. I'm kind of ignoring the presence of the double bond. You might be wondering, isn't that a substituent? Should I be naming it? Double bonds and triple bonds aren't substituents. They're just a feature of the carbon chain. So they are going to be included in the name, but because they are not substituents, they're not going to be coming at the beginning of the name. Alphabetize our substituents. So we have 2-ethyl, 4-methyl. And now let's take on the task of naming this carbon chain. This is a 5-carbon chain, which is a pentane, but it has a double bond in it, which means that it's not a pentane, it's a pentene. But it has an alcohol on it, which means it's not a pentene, it's a pentenol. We have to locate the position of the ene, and we also have to locate the position of the ol. And this is one of those times where numbering in the middle of the name is really, really handy. Even though numbering in the middle of the name is not my favorite, this is a situation where I'm thankful that we have this option. If I had to put the numbers at the beginning of the name to locate the position of the "-ene" or the "-all", it might be a little bit tricky. Is the "all" on the 4 or is the "all" on the 1? Where is the "-ene"? Is it on the 4 or is it on the 1? By putting the numbers in the middle of the name, I'm able to communicate very clearly that the alkene is on carbon number 4 and the alcohol is on carbon number 1.